Good day, dear colleagues. I present a group of authors, Hilgurt, Taraspechko, Harchenko, and the topic after reviewing sounds as follows: parallel simulation environment for planning the development of electric power systems under terrorist and military threats. Here you can see the content of the report. And about motivation, the threats to electric power systems can be divided into non-targeted natural threats, such as technological or anthropogenic, and targeted terrorist threats, military threats. Traditional challenges to ensure the reliability when we speak about non-targeted threats are sustainability, robustness, durability, resilience, and so on. But if we deal with targeted threats, we need to have another tools, another means, and the main tool to resist targeted threats is to ensure the structural reliability property of an electric power system. What is it? Structural. What it is? Structural variability. As a result of terrorist military attacks, the connections between the components of electric power system are destroyed, and it becomes divided into separate energy islands. And structural variability is ability of electric power system to form a number of regional subsystems and connections between them. Structurally variable EPS deals with various types of generating capacities in each local energy subsystem. There are renewable and advanced nuclear technologies, solar power plants, wind power plants, nuclear, and so on, and different kinds of storage systems. Battery storage, gravity, hydrogen energy storage systems, pumped hydroelectric storages. In order to effectively plan and development structural variable electrical power systems, correspondent adequate mathematical models are needed. Such models describe classic, well-known unit commitment problem and are mathematically formulated as a mixed integer linear programming problem, MIL problem, with the objective function of minimizing system costs. Solving such problems on a countrywide scale using existing software solvers based on conventional single processor computers requires a large amount of computations to obtain result of simulation within an acceptable time. It is necessary to use parallelization methods and high-performance computing HPC technologies. So the objective of this research to develop a general concept and a structure for a parallel simulation environment for solving simulation tasks of structurally variable electric power systems under terrorist and military threats, so that this environment would be suitable for restoration and optimal development of Ukraine's energy infrastructure during the war and in the period of post-war reconstruction. Analyzing the state of the art in the field of HPC and development of simulation environments shows that many researchers was fulfilled beginning from the middle of 1990s. After analyzing these works, we can summarize that creation of parallel simulation environments compared to a universal system, more effective solution gives dedicated developments, not universal systems. Such environments are focused on a relatively narrow class of tasks, taking into account and effectively utilizing the specific features and characteristics of particular objects and particular models. So in this work, the authors did not propose their own solution in field of constructing simulation environment. Instead, well-known development served as a basis on which the research was grounded. We focused attention on the unique characteristics, features, peculiarities of the simulation task related to planning the development of electric power systems under terrorist and military attacks. And based on these specific characteristics, the requirements for the simulation environment were formulated, which guided the development of this concept and structure, multi-layer structure. The main feature we can name necessary to simulate local subsystem, energy subsystem, and a state unified energy subsystem level. The creation of appropriate algorithmic and software tools require tremendous effort and time. Therefore, users typically use the result of such developments in the form of so-called solvers designed for mill tasks, mill task solvers. The information contained in such models is another feature. Is difficult to store and very come with some not useful to manage. Requirement to the simulation environment. They requirements for simulation arise from its specific features. The environment should include models both for state unified energy system and local energy systems. It should include cluster mathematical models for power plants, solar, wind, nuclear, and different storage systems. The mathematical models must be enable to predict EPS load modes in short-term and long-term planning tasks. Must support use of solvers, free and commercial solvers. To utilize HPC resources as effectively as possible. This environment must provide research capability, provide high flexibility to ensure the implementation of different approaches to parallelizing computations. Must be able to support various protocols, data formats for the alignment and exchange of parameters and actual data. Must be able to use high performance computing resources of various classes, of various types. Here you can see the general structure of the simulation environment proposed. It has multi-layer structure. Let us briefly consider each layer. User layer provides interaction between users and almost every other layer of the environment. It is have been implemented as a web service. If all required models and algorithms are available within the environment, the ideal case, users only need to upload configuration files. In other cases, user layer allows to upload custom software components and creates and run its own scripts to manage the computational process. Mathematical model layer contains mathematical models. Let us consider it later. Presentation layer provides supporting different formats by various MILP solvers, as well own formats of data. Software layer contains high-level programming languages. As the main programming languages are used here, Julia platform, Julia high-level programming language. It scopes whole problem solution process from input data, from loading input data to storing results.
Sorry, sir, you have 2 minutes for finalizing your presentation.
Okay. Model layer contain models. Parallelization layer includes algorithms and their realization as classic, so-called, for example, Bender's decomposition, and intellectual algorithm, evaluation central algorithm, and colony, and so on. Solvers can be used in single-thread mode, multi-thread mode, and multi-node mode. At technology sub-layer, we can use only solvers as well, OpenMP technology, MPI technology, and so on. There are many formats for data presentation which solvers use. Unfortunately, sometimes it is necessary to use a dedicated structure. Here we use OpenXML spreadsheet for data exchange. It don't be useful to have the same file for initial data and to write results. A case study was realized to test the proposed solutions. Computation results was presented in the previous presentation, one before the last. We only pay attention that the combination of using skip and evolutionary centers algorithm realized by the meta-heuristic software package gives 1.5 times speed up, and combination of ESA with high GSS solver gives even 7.5 times acceleration. Conclusions and future work. The concept of a parallel environment for modeling a structural variable electric power system under terrorist and planetary threats is proposed in this study. The main goal was to reduce wall time to acceptable levels. Also, the acceleration achieved was relatively modest. It still confirms the viability of the proposed concept. Such modest results of accelerating by parallelizing mill task indicate a pressing need for simulation environments such as the one proposed in this work. And in future, other components and models will be realized. MPI technology and other multi-node approaches will be explored. more complex and comprehensive experiments will be carried out. Thank you for the attention.
Thank you, Sergey, for your presentation. Do you have any questions, colleagues? No questions. We have listened to all the reports of our program. The time of our workshop is over. Maybe have some comments. There is no. Thank you for your collaboration and goodbye.
Goodbye.
Thank you.
Thank you.
Thank you. Bye.
Thank you. Goodbye. We are starting tomorrow morning at 9:30 at the main plenary section.